Hi everyone, welcome back to this control system lecture. In this video, I'm going to demonstrate how do we design a lead controller to achieve the time domain specifications of settling time and maximum overshoot. There are a few ways of designing the lead controller, but as we can see over here, the requirement that we actually face here will be the time domain, settling time and maximum overshoot, which are related to the roots, the dominant roots of a system. Hence, in this case, by looking at the specification that we need to achieve over here, we will be using the root locus approach. And this, for simplicity, I'm going to set the settling time to be exactly equals to 0.5 and the maximum overshoot to be exactly equals to 5%. So even though it says it's a less than, but just for the sake of the demonstration here, we will just stick with 0.5 and 5. Okay, and basically the configuration of the systems will be something like this. Okay, as usual, we have our RS, which is our unit step response, unit step input. Okay, which has an amplitude of 1. And then followed by C. So C will be our compensator. In this case here, we'll be using lead compensator. G will be our plant, and then Y will be our output. And what we expect from Y here is that our settling time will be less than 0.5 and maximum overshoot is equals to 5%. To begin with the root locus approach of the lead compensator, we will need to actually use the root locus criterion, which is the angle criterion and the magnitude criterion. But before that, the very first thing that we have to do here is that we have to transform these two, okay, the requirements here into our desired roots. Okay, and this desired roots here we will actually treat it as a SD. And SD, we have the form of a zeta or negative zeta omega n plus minus j omega n squared of 1 minus zeta squared. And as you can see here, we need the information of the zeta and omega n, which we are going to determine from the settling time and maximum overshoot criterion. So let's do this. Okay, so the maximum overshoot will be equals to this expression, and as you can see here, we have only one unknown, which is our zeta value. We are going to substitute this 5% into here, and I'm going to reverse this entire thing to get our zeta value. So please follow the following calculations here. Just a little bit explanation on these steps here. The maximum overshoot as from the requirement is 5, and following the expression, and we have an exponential here. To get rid of this, we will be using the ln function. So ln 0.05, we extract the power terms in front and left with the ln e, which basically will be equals to 1. And to eliminate the square root here, we're going to square both sides, and we're going to end up with this expression. Just by rearranging and solving the zeta value, we are going to have a 0.6901. We'll be using the zeta value to sub into this settling time formula for us to obtain the omega n value. Okay, we have obtained our omega n value to be equals to 11.5925, and with the zeta of 0.6901, we can actually combine these two into our desired SD, okay, which will be equals to negative zeta omega n plus minus j omega n 1 minus zeta square, which will eventually to be this. We will have these desired roots to be negative 8 plus minus j 8.3897. Very obviously from here is that we will be able to only use the lead controller. That means that we will not be able to use the gain adjustment to actually achieve the specification. So why did I say that is that if you consider the original root locus, which is going to be something like this. Okay, so we have a 2 pole minus 1 minus 4, and then this will be the root locus of the original system. So if we use the gain adjustment, no matter how we adjust, we can only adjust the closed loop post along the crosses here. And if you look at our desired roots SD and SD, which is located at -8, that means no matter how do we adjust the gain, okay, we will not be able to shift it to the SD. So what we need to do here is that by using the lead controller, we are going to add the poles and zeros somewhere around here, so that the resultant root locus can actually pass through the SD, something like this. Okay, so we're going to bend the root locus so that it can pass through SD. By bending the root locus through introduction of additional pole and zero, we will actually ensure that, okay, the root locus will still satisfy the two criteria that I mentioned earlier, which are, okay, angle and magnitude criterion. The angle criterion states as if you are actually considering a compensated system, the angle of CG at the location of your desired SD must be equal to -180. And then the magnitude criterion states that the magnitude of CG also SD must be equal to 1. We'll be using these two criteria to determine what will be the zeros and the poles of the lead compensator. So by the way, we are going to set this, our CS, to be equals to K S plus Z over S plus P. So this is a simple format that we'll be using to represent our controller, the lead controller. So let's begin from the angle criterion. So the angle criterion states that the angle of K SD plus Z over SD plus P multiply 10 over SD plus 1 and then SD plus 4 will be equal to -180. Now you can imagine that here we can actually skip these two terms, which is our K and 10, simply because these two terms will always give us 0 degree. As we have learned in the Bode plot here, pure gain, okay, will not contribute anything in terms of the angle. And after solving the SD, remember SD just now we have determined, okay, we come back to here, SD is -8 plus minus J 8 point something, and if we substitute everything into this expression, okay, we are going to end up with an equation with two unknowns, which are the Z and also P, the zeros and the poles of the controller or the compensator. In this case, you can actually imagine that to solve this, we will have to set one of the values. Okay, so a normal approach that we actually trying to use here is for convenience. Okay, you can find a lot of other methods that is described in a lot of control theories. Okay, but for the demonstration here, we are just going to set the zeros to be equals to one of the poles here, either -1 and -4. To be safe, we will choose to be -1. So the reason why we want to choose that is because of the pole 0 cancellation. Okay, so this will actually reduce the order of the compensator system to make it easier for us to manage. And at the same very good thing here is that it will actually ease our calculation. Okay, so let's work it out by setting the, okay, Z is equals to 1 to cancel with the SD plus 1 here. Okay, the expression for this angle criterion will reduce to the angle of SD plus P minus the angle of SD plus 4 must be equals to -180. So we're going to calculate this angle of SD plus 4. So how do we calculate is that, okay, remember when you're actually trying to find the angle, you have to find the angle that contributes for the complex term. That means you have to take into consideration of the real part and imaginary part. So SD is given to be -8 plus minus J 8 point, okay, let's refer to above, 8.3897. Okay, 3897. So after you substitute in, this entire complex term will now be located at the second quadrant with a real part of -4 and imaginary part of 8.3897, and the angle that we are supposed to find will be this angle. Therefore, this entire expression, okay, will now become SD plus P minus 180 degree minus inverse tangent of 8.3897 divided by 4, and it must be equal to -180. Okay, so we'll be using the same approach here to determine the value of SD plus P later. Okay, so for now, let's complete this expression. Okay, we have completed the computation of our pole, which in the end will be located at 12, which means to be more accurate, it is actually -12 on the left hand side of the S-plane, by setting the 0 to be equals to 1. We are going to substitute these two values into the magnitude criterion, okay, and we're going to set it to 1 so that we can determine our last parameter of this lead compensator, which is the gain. So we're going to have the magnitude of K SD plus 1, SD plus 12, multiply our plant, SD plus 1, multiply SD plus 4 equals to 1. And as mentioned earlier, one thing good in here is that by setting the value of the 0 for the pole 0 cancellation, you actually ease our calculation. So these two terms will be cancel off each other. So our gain here, okay, will be actually equals to the magnitude of SD plus 12 multiply the magnitude of SD plus 4 and divided by 10. And remember, okay, one thing that you have to remember here is that when we are talking about the magnitude, it is actually equals to the square root of the real square plus imaginary square. Okay, so if we imagine our SD is equals to -8 plus J 8.3897 and we plus 12, the real part will become 4. So the magnitude of it will be 4 square plus 8.3897 square, and we need to multiply with the SD plus 4, the magnitude of SD plus 4, which after you have substituted in the SD, it will also give us 4. But of course, -4 square, I don't care so much in here. So the 4 here is actually -4 square, okay, but eventually it will result in the same thing, okay, 3897 square and divided by 10. Okay, so finally we will have this. Okay, so by calculating this here, at the end our CS will be equals to 8.36387 S plus 1 divided by S plus 12. Okay, so this will form our simple lead controller that now we are going to use the MATLAB to actually see how good the performance of this lead controller with respect to the specification that we should observe earlier, which is our settling time must be equals to 0.5 and maximum motion must be equals to 5. Okay, so let's look at the MATLAB. In MATLAB, we define the variable G as our plant, okay, with a 0 pole gain of no zeros and 2 poles -1 and -4 with a gain of 10, and our controller or the compensator C with a pole of -1, 0, 0 and -1, pole and -12, and this is a forward gain. And then we are going to feed back these two to form our T, and finally we type step T to generate the step response. So let's look at the output now. Okay, so you can see that the actually overshoot here is actually very good. Okay, exactly equals to 5 that we actually predicted here. And settling time, we have a minor discrepancies here that 0.517. Although we actually designed it to be 0.5. Okay, but the discrepancies here is actually quite small, so we'll treat it as acceptable. Okay, so I have demonstrated how do we design a simple lead controller using a selection of 0 for the pole 0 cancellation, one for convenience, and next is actually to reduce the amount of poles to actually reside in the system that can affect our prediction on the output. Okay, so in the next video, I'm going to explain more, especially on the lead lag controller, especially on the lag part. Okay, so thank you very much for watching. Bye.